Hey everyone, welcome back to Math 256. This is Scott. Let's get started. We are now going to take on the subject of a new chapter which has a strong relationship to the material of the previous chapter in ways that we'll see presently. So first off, section 4.1 here, in which we will be looking at homogeneous linear equations. And actually, we'll be looking at something even more specialized than that, in fact. But this is the title, as announced in the textbook, so we will copy that. But here is our actual setup. So it's in fact something even more specialized than this. We are going to be looking at a second order linear homogeneous ODE with constant coefficients. So in particular, let's just say we are talking about y double prime plus, and we can just say here b y prime plus c y equals 0. So what makes this second order hopefully is clear. It is degree 2 as far as derivatives go. What makes this linear, hopefully you can kind of suss out by the fact that we have, in terms of the y's, only y's and its derivatives, nothing like a y squared or a square root of y or anything like that. Now for the homogeneous, that's what the 0 gives us. So this is what makes it homogeneous. And then for the constant coefficients, b and c are constant. So this fits the pattern of linear equations that we've seen, but this is more specialized, because with the linear first order equations, the factor here on the y was capable of being something other than a constant, and we had over here what we would call a q. Okay, so now our goal is to solve these, and let's think about this for a second. All we're taking are derivatives of y, and when we do this, all we're producing are combinations of this that equals 0. So any solution would have to fit this pattern. So just as a quick note, if we look at a function of the form, let's say y equals c e to the rt, and plug it into the differential equation, we would get the following. Alright, so if I want to plug it into the equation, I would have to, I'd have to take the derivatives of y, so y equals c e to the rt. Y prime would equal r c e to the rt. Y double prime would equal r squared c e to the rt. It would just be a matter of multiplying these out. And then in our differential equation, if we plug these things all in, we would get so for y double prime, we get r squared c e to the rt plus b r squared c e to the rt plus c, sorry, not r squared, just r, I should say, plus c, capital C, e to the rt, and that equals 0. And then if we take this and divide everything by the capital C and the e to the rt, thus r squared plus br plus cr, or plus just c, equals 0. And what this means is that equations of the form that we have identified will be solutions precisely when the value of r satisfies this equation. So then, functions of the given form, that's c e to the rt, will be solutions whenever r satisfies the equation r squared plus br plus c equals 0. And this is actually called by a name that we've heard before. This is called the characteristic equation for the differential equation. So this is called the characteristic equation for the ODE. And if it seems confusing to you that this would be a phrase that we've used before in the context of eigenvalues, then we can rectify that confusion by noting a particular fact. It is exactly the same as the characteristic equation we would get if we converted this to a system and found the eigenvalues, and is exactly equivalent to the equation we would use to get the eigenvalues of the corresponding system. Okay. So then, our approach. our approach. Given y double prime plus by prime plus c equals 0, solve the characteristic equation to produce solutions of the form y equals, and this would be the general case, c e to the rt, and then depending on the circumstances, we may we have several different ways that this can be elaborated upon. So the different possibilities. So 3 different cases. And these are the 3 cases that correspond to the situation with eigenvalues and such. 3 cases. So 1. Two. Distinct real values of R. Then our general solution is y equals c1 e to the r1t plus c2 e to the r2t, and we would solve for the c1 and c2 based on initial conditions if they were given. With initial conditions. For y and y prime. And typically these will be initial conditions of y equals 0, or y of 0, and y prime of 0. Okay, so this is case 1. This is sort of the default case. But then, whenever we are not in this particular case, then we have one of 2 other possibilities. Either we have 2 complex solutions, alpha plus beta I, or plus minus beta I, then what we can do is actually pretty much the same thing, or it's not the same thing that we would do in the case of complex eigenvalues, which is to appeal to Euler's equation. So Euler's equation here, once again, is going to be that e to the alpha plus beta I times t is equal to e to the alpha t plus e to the beta t I, times, which is going to be equal to then e to the alpha t times cosine beta t plus I sine beta t. And so then what we're going to essentially do is create the two solutions out of the following. So then the general solution it basically comes from taking the real and imaginary parts of this, just as we have done before. Y is equal to C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. So the real and imaginary parts of the general solution that we would ordinarily produce is what we will use here to find our two linearly independent solutions. And then finally, the third case. So case 1, we had two distinct real values of r, and those formed the two terms c1 e to the r1t plus c2 e to the r2t. Case 2, we had two complex solutions, and this is just going to be broken down according to typical Euler shenanigans, and we have produced two terms very similar in spirit to what we've done with the eigenvalue situation. And in case 3, this is the case of a single repeated solution. So a repeated solution. So r equals just one particular value with multiplicity 2. So r equals, so let's say just r equals, let's just say multiplicity 2. Okay, so then the format of the solution here is going to be as follows. So we can make one branch of the solutions for free by just using what we have already been doing. If r is a solution to the characteristic equation, then this will be a solution to the differential equation. And so it is not, there's nothing out of the ordinary about this term. Now, the part that is out of the ordinary is the next term here. And we'll see why this works in a second here. But C2t e to the rt. So we give an extra factor of t to the term that we already had, and let's see what happens. And why this works. Okay, so now let's ask ourselves, why does this work? But what we're asking when we ask this question is really just why the second term works. The first term fits in the same pattern as what we've been doing, so i.e. y are things in the form of this solution. So y is ct e to the rt, a solution. Alright, well, to answer this question we have to think a little bit more about what it means to have a multiplicity 2 solution to our characteristic equation. Or just in general, what is the deal with multiplicity 2 solutions overall? So here's just a little note. If, let's just say x equals r is a multiplicity 2 solution to the equation I was going to put ax squared, but there's no reason why we need the a here. We can always just assume that the constant coefficient has been divided by. So x squared plus bx plus c equals 0. Then x squared plus bx plus c is the same as x minus r squared. And what that means then is that if I take the derivative of both sides, so if I differentiate both sides of this, I would have 2x plus b is equal to 2 times x minus r, which is just interesting to note. All right. So then if I plug in if x equals r, that'll give me 2r plus b is equal to 0. Duly noted. Alright, so then take y equals c t e to the rt, and we'll take its derivative and its second derivative. We'll run them through the differential equations ringer and see what happens. So then, the derivative, this will require the product rule here. So then y prime will be c e to the rt plus, and then it's going to be ct times the derivative of e to the rt, which will be crt e to the rt. So be it. And then y double prime would be the same process repeated here. So we're going to have cr e to the rt by the chain rule. For here, we're going to have the product rule again, with this time crt as the first of our functions. So that's going to be cr e to the rt. Plus, now leave the first alone and take the derivative of the second, so it's going to be crt times e to the rt, well actually times the derivative of e to the rt, which is going to bring down an extra r, which is going to make that cr squared. So that's going to equal, so what's it going to be? It's going to be 2 cr e to the rt plus cr squared t e to the rt. Okay, so now we will plug these pieces all into the original differential equation and see what happens. So if we plug these into y double prime plus b y prime plus c y equals 0, then let's just check. So we'll get here 2 cr e to the rt plus cr squared t e to the rt plus b times c e to the rt plus b times crt e to the rt. Duly noted. and then plus c times y, which is going to be t e to the rt. So now we're just kind of hoping this is all going to equal 0. Well, if we separate out the terms that have the e to the rt and the terms that have the t e to the rt, then we can break this up. So let's rearrange. Or actually, better yet, first how about we just divide everything by the common factors of c and e to the rt. Every term here has that, so let's just divide by that. So if we divide everything by that, we'll have just 2r. 2r plus r squared t plus b plus br BRT, I should say. BRT plus what else? C, no, not C, plus just T. Oh, sorry, this is little c. Little c, capital C. Unfortunately, our letters it's a little awkward having two different c's involved in the same equation, but it's standard for both polynomials and for the differential equations. So this is c t equals 0. Okay, so now let's look at what we've got and see what we can say. So first off, if I take the terms that have the t and the terms that don't and separate those out, then I'll have just t times r squared plus br plus c, and then for the terms without the t, that's going to be 2r plus b. But since r is a solution to the equation, that means this equals 0. So this equals 0 by definition, and this equals 0 by our note. So then what that means is we have 0, so 0 equals 0. Check. So thus we have solution formulas for all three scenarios. Scenarios. So let's just try some examples. Alright, so for our first example here, example A, we will take a differential equation with some initial conditions as well. So let's say here our differential equation, and we're going to try to mix up the way we write these, throw in lots of primes and also lots of the Leibniz notation. So we'll say d squared y dy minus 4y equals 0. And then for the initial conditions, we'll say y of 0 equals 2, y prime of 0 equals 0. Okay, well, let's try this. So derivatives of y correspond to powers of r. So r to the second minus 4 times r to the 0, so it's the 0th derivative, is equal to 0. So this means then r equals plus or minus 2. So if we think about this, you can solve it by factoring into r plus 2, r minus 2, or r squared equals 4, which then implies that if you take the derivative of both sides, you get the plus or minus 2. Okay, so then that gives us the basic formula y equals c1 e to the 2t plus c2 e to the negative 2t. Okay, so be it. And then if we want to plug in the initial conditions, we'll need the derivative of this as well. So this will be 2 c1 e to the 2t minus 2 c2 e to the negative 2t. So then if we plug in t equals 0, we'll get so y of 0 equals 2, y prime of 0 equals 0. So that means 2 equals mystery c1 plus mystery c2. And by the same token, c from the y prime we'll get 0 equals 2 c1 minus 2 c2. Alright, and if we wanted to solve this for the values, we can see that this implies that c1 and c2 are equal to each other. So this implies that c1 equals 1, c2 equals 1 as well. So if you can solve this by any number of means, including linear algebra means, but the important thing is somehow or other you find a value for c1 and c2 using these two initial conditions and the formula as originally or as you have found it. Okay, so then that gives us our solution of y equals just e to the 2t plus e to the negative 2t. Now, while we're here, might as well point out that when we are solving these by this method, we have actually in our toolkit the ability to solve it by an alternative method as well. And that alternative method would be convert this the second order equation into a system of equations, and then we can solve it by our eigenvalue methods that we've explored so thoroughly. All right, but now let's actually take this example and make a slight change to it and see where that takes us. So example B. What if instead of y, the second derivative of y with respect to t minus 4y, what if we have d squared y dt squared plus 4y equals 0? So it's a very similar, oh, I just noticed in my original equation here, miswrote that. I got so excited about getting the top in Leibniz notation, I messed up the bottom part here, so it should be dt squared. As written, it didn't really make any sense, actually. Okay. So here, the important thing is second derivative. So here, let's say we have this, and let's say we have y of 0. Let's just have the same two initial conditions. Y of 0 equals 2, y prime of 0 is equal to 0. Okay. So now, once again, we quickly leave behind the actual differential equation and turn it into just a little algebraic equation as our first step here. So r squared plus 4 equals 0 will be our characteristic equation, written now in terms of r instead of in terms of lambda, as we may have seen before. And then, once we have this, then we are going to solve this for the r. You can use the quadratic formula if you want, but it's easier if we just go r squared equals negative 4. So then r equals plus or minus 2i. And so then what that means is c is equal to, so we've got basically c1 e to the 0t cosine of 2t plus c2 also e to the 0t sine 2t. But those e to the 0t's are not getting us anywhere, so then these just equal 1, so it's going to be c1 cosine 2t plus c2 sine 2t. Oops, cosine 2t plus c2 sine 2t. Alright, then if we want to plug in the initial conditions, we'll need to first find what y prime is. So y prime here is going to be the derivative of cosine is negative sine, so with the chain rule it's going to be negative 2 c1 sine 2t plus the derivative of cosine is going to be, the derivative of sine is going to be cosine. The chain rule is going to bring out the 2, and we're going to have therefore 2 c2 cosine 2t. And now we will plug in y of 0 equals 2, y prime of 0 equals 0, and that means we're going to have 2 equals c1. So here cosine is the only thing that survives, equaling 0. They're plugging in 0, I should say. And then over here we'll have 0 equals negative 2 times, is going to equal 0, plus 2c2. So what's this going to mean? This is going to mean that c1 is going to equal 2, c2 is going to equal 0, and so that gives us, for our overall equation here, that just gives us a solution y equals 2 cosine 2t. Which, sure enough, if you think about it, the second derivative of cosine 2t is going to be equal to first you pull out a 2, so that'd make it 4, then you'd pull out another 2, that'd make it 8, and that would sure enough be equal to 4 times the original function. And similarly, the initial conditions are both also what you would get when you plug those into here. Alright, so we've seen now a case of two distinct real solutions, two distinct complex solutions, in this case actually purely imaginary solutions. So this would correspond, by the way, to just a stable center from the language of our earlier investigations. But now let's look at the third case. That'll be d squared y over dt squared plus 4 dy dt. You know what? I'm getting tired of the awkwardness of Leibniz notation. We'll just switch over to primes here. Y double prime plus 4 y prime plus 4y equals 0. And we'll just keep those same two initial conditions that we have been that we've been using. Y of 0 equals 2, y prime of 0 equals 0. Well, when we want to switch over to the characteristic equation here, what we would get is r squared plus 4r plus 4 equals 0, which leads us to r equals, or I guess we'll say r plus 2 squared equals 0, which means that r equals negative 2 with multiplicity 2. Alright, well, if that's the case, then that means that we are going to have the third case here of our solutions. That's going to be C1 e to the negative 2t in this case, plus C2 t e to the negative 2t. And then for our y prime, that means we're then going to have negative 2 c1 e to the negative 2t. For the second term here, it's going to require us to use the product rule. So here we'll say plus c2 e to the negative 2t plus looks like negative 2 c2t e to the negative 2t. And then if we plug in y of 0 equals 2, y prime of 0 equals 0, and we see what we get here. We would get 2 equals c1 plus c2. Okay, that's a familiar result for us to get. But then what about for the other one? That's going to be, looks like 0 equals negative 2 c1 plus c2 plus 0. That last term will equal 0 when you set t equal to 0. And so now we have a slightly different outcome from before. So it's going to be c2 equals 2c1, which then means that we're going to have 2 equals c1 plus 2c1, which means c1 is going to equal 2 divided by 3, and we're going to have c2 then is going to equal 4 divided by 3, and that means that our y is equal to 2/3 e to the negative 2t plus 4/3 t e to the negative 2t. So this was a case of repeated solutions to our characteristic equation, which leads to a term of the form of t e to the negative 2t. That's the main takeaway here. Now, what happens when the equations that we're solving do not come out quite as nicely as these ones? So let's take another example here. So let's say D. What if the equation has the form y double prime minus 8y prime plus 5y equals 0, and we have y of 0 is equal to, and we'll just make this nice and messy, 3, y prime of 0 will equal 2. So this is going to be, this has not been, this one has not been run through the usual filters of producing nice answers. Here we are just looking at an equation in the wild that's capable of being as messy as we like. So, what's that going to produce then? Well, then we just go through the same process here and see where that takes us. So r squared minus 8r plus 5 equals 0. If this were a carefully curated equation, then we could expect maybe that we are able to factor this. But here we can see that we cannot factor this. Go ahead and try. Okay, well, in that case, r is equal to, and it's just going to be the quadratic formula, 8 plus or minus the square root of 64 minus 4ac, so it's going to be minus 20, divided by 2a, it's going to equal 2. And what's that going to be? 8 plus or minus the square root of 44 all over 2, which is equal to 8 plus or minus square root of 4 times 11 over 2, which is 8 plus or minus square root of 4 times 11 is the same as root 4 root 11. It's going to be 2 root 11 all divided by 2, and here we can distribute that 2, and we get equals 4 plus or minus the square root of 11. Well, great. So that's where things stand. That is the that is what we get as the solutions to this equation. So be it. And then we just have to now see where that takes us. So y equals c1 e to the 4 plus root 11t plus c2 times e to the 4 minus root 11t. And you could have done them in either order. It doesn't really make any difference. The answers would then just correspond to alternating the c1 and the c2. Alright, and now if we take the derivative of this, what's that going to give us? It looks like it's going to give us 4 plus the square root of 11 c1 e to the 4 plus root 11t plus c2 plus, I guess I'll do it in the same order, 4 minus root 11 c2 e to the 4 minus root 11 t. And if I use the y of 0 equals 3 and y prime of 0 equals 2 initial conditions, then let's see where that. Then what we will do is produce a system of little equations here, and we'll decide what to do after that point. So 3 is equal to, just going to be c1. When we plug in t equals 0, then then we'll just have e to the 0. And then we have plus, by the same logic, c2. Okay, so that's all well and good. Now for the y prime, we're going to have 2 equals, and it's just going to be 4 plus square root of 11 c1 plus 4 minus square root of 11 c2. Well, unfortunately here we have these rather ungainly expressions, the c1 and the c2 involving the 4 plus the square root of 11 and the 4 minus the square root of 11. What would usually happen in practice is we would just probably settle for a decimal here, You can do this algebraically by just treating each of these as an expression and doing what you have to do, but it's not really worth it. So here we'll just put it into any kind of calculating device, get an approximate decimal, and that'll be what we'll do. So we'll say 7.3166 C1. And here what we'll have is for minus square root of 11, it's going to be just 0.6834 C2. Okay, so that's how we'll deal with this when we have these messy expressions that involve radicals. It will usually be to our advantage to just change it to decimals and work from there. This doesn't look very clean, but it'll be cleaner than something that has a big constellation of square roots of 11 in it. Okay, so now how do we solve this? We can do it by substitution. So for example, C1 is equal to 3 minus C2 from the first equation. And then if we plug that into there, then we'll have 2 is equal to 7.3166 times 3 minus C2 plus 0.6834 times C2. Then what's that going to give us? It looks like it'll give us 2 equals 3 times that. So once again, if I take that and I just multiply it by 3, what's it going to give me? So it looks like it's 21.9498. So 9499 if I round it accordingly, according to the fourth decimal place as I've been doing, minus 7.3166 C2. C2, and now if I just take this number, so I'll just try to remember where these numbers came from, and I will subtract them accordingly in the calculator just to prevent any furtherance of rounding issues. Do not want to compound rounding problems. So you can just take the numbers as they are, or you can take them as they were produced by the calculator. But the important thing here is we have 2 equals 21.9499 and minus 6.63. 2. So if I want to solve this for C2, I will just add this to both sides, subtract 2, and divide, and that'll give me C2 equals, so it's going to be 19.9499 divided by 6.6332. And that gives me C2 equals 3.00758, so 76. So C2 apparently equals that. And then C1 then, based on what we can see here, is going to be very small, but negative. So it's going to be negative 0.00758. Here, let me just not be a hero here. 3 minus answer. Yeah, okay. 0, 0, 7, 6. So this is what happens when you have uncurated C1 and C2, is you are liable to end up with something that is actually quite lopsided in its values. So what we get here is y equals negative 0.0076 e to the well, so it was the 4 plus those 7.3166 t, and then plus 3.0076 t e to the, this is the other exponent, 0.6834 t. So this was again an approximate solution. If you were not satisfied with an approximate solution, if you demand exactness in your answers, then you could repeat my calculations here, never resorting to a calculator and leaving things in terms of root 11 and see what you get. It's not as messy as it seems, but it's still a bit of a hassle. Okay, so this is what happens when it doesn't work out very nicely for two distinct real solutions. Now let's look at the case of complex solutions, where it doesn't necessarily work out so cleanly. Maybe not as messily as this, but not cleanly nonetheless. And as an extra little twist here, let's vary the format of our equations ever so slightly. So this appears not to be in the same form as the ones we've seen before, but the same approach will still work. So if we have y double prime plus 6y prime plus 4y equals 0 with initial conditions y of 0 equals 3, y prime of 0 equals 4, then at first glance it looks like what we have here doesn't quite fit the formats of our second order homogeneous constant coefficient linear ordinary differential equations. However, the same approach still works. If you divide everything by 9, you would get the characteristic equation, which you could then multiply by 9. So it turns out the characteristic equation can just still be taken verbatim from this equation, just taking the coefficients of y double prime, y prime, and y as the coefficients of r squared, r, and the constant term respectively. So this is where things stand now, and this produces an equation that we could actually you could conceivably factor this, and it wouldn't be necessarily the worst idea to do so. However, if we can't factor it, which would be usually the case, then we would want to go to the quadratic formula. So let's just see how that would go. So here now, the way this would look if we wanted to use the quadratic formula is r equals -6 plus or minus square root of b squared, which is 36, minus 4 times a times c, which is 9 times 16, which is 144. And then that is divided by 2a, which is going to be 18. Alright, so here let's just think about the expression we've got, and once again, not to be a hero, I'm just going to use a calculator so I don't make a silly blunder from the arithmetic side, and that's -108 in the radical. So we might as well put that in, -6 plus or minus square root of -108 divided by 18. Now both of these are in fact divisible by 36, so I expect the result to be divisible by 36 as well. And so I'll divide it by 36 and make sure. Sure enough, it's 36 times negative 3. So this is equal to negative 6 plus or minus square root of 36 times the square root of negative 3, I should say, all over 18, which is equal to then negative 6 plus or minus 6 root 3i, all divided by 18. And so if I divide the top and bottom of this all by 6, I would get negative 1/3 plus or minus 1/3 root 3i, or root 3 over 3, alternatively. But the important thing is here we have an expression that we weren't able to completely resolve in terms of the square roots and such, and so we'll just leave it as it is here, and we can then try plugging in the initial conditions and seeing what those give us. So here's where things start to get messy. So this is about to get messy. So far it doesn't look so bad, but even in a case like this where we were mostly able to produce we were able to simplify the radical expression down quite a bit. Even so, we're about to get into some spots where the derivatives are going to start getting pretty unwieldy. So here's why. If we take the basic form of our solution, we're going to have y equals c1 e to the negative 1/3 t cosine, and I'm going to rewrite this as root 3 over 3t. So that's just following the basic format of our solutions for cases of complex solutions to the characteristic equation. And then c2 e to the negative 1/3 t sine of root 3 over 3t. So this is all by the book. Now, if I want to plug in initial conditions, however, I am going to have to deal with the situation of using the product rule to find my derivatives. So let's just go ahead and try this. So when I do this, I'm going to have C1 times, and I'll just do it as it appears here, and then I'll simplify it in the next line. E to the negative 1/3 t cosine root 3 over 3t. So we won't try to be heroes simplifying this along the way. We'll just let it be messy, and then we'll simplify it in a second. Plus, what are we going to have? C1 e to the negative 1/3 t. So far, according to the product rule, we have differentiated the first factor. Now we have left the first factor alone. And what are we going to have? We're going to have negative root 3 over 3, and then it's going to become the sine root 3 over 3 t. And is that everything? Looks like it. So then now for the second term, we're going to have something very similar. It's going to go c2 times negative 1/3 from the chain rule times e to the negative 1/3 t. And then for the first installment here, we're leaving the second factor alone, so it's going to be sine root 3 over 3t. And then for the last one, it's going to be c2 times, and then what's this going to be? We are leaving the e to the negative 1/3 t where it is, And we are now multiplying by the derivative of the second function here, which is going to be root 3 over 3 comes out from the chain rule. And now it's just going to be cosine root 3 over 3t. Alright, now when it comes to this whole expression, if we are talking about the initial condition, that is where the t equals 0, and the only factors here that will survive are the ones that have cosine in them, not the ones that have sine. So if we look over these and we see where what we're gonna get, we'll see negative 1/3 c1 for that one, and that's it there. And then over here we're going to see plus root 3 over 3 c2. Okay, so according to our expressions here, this is what we will get. And now if we look at our initial conditions, they will tell us that the original value here was equal to then it was y of 0 equals 3, y prime of 0 equals 4. And now if we put the pieces where we have them, then we'll have, so 3 equals, looks like just c1 plus 0, which is nice. And then 4 is equal to negative 1/3 c1 plus root 3 over 3 c2. So if I note from here that this implies that c1 just equals 3, then that means if I plug that into here, I'll have 4 equals negative 1/3 times 3, which is negative 1, plus root 3 over 3 c2, which then if I add 1 to both sides here, root 3 over 3 c2 is equal to 5. And if I multiply both sides by the reciprocal here, that would give me c2 is equal to 5 times 3 over root 3. But 3 over root 3 is actually something we can reduce, because 3 is the same as square root of 9, or in other words, root 3 over root 3, so those cancel, and that gives us just 5 root 3. So 3 root 3, 5 root 3 is what we get for C2, and then that gives us our overall solution here. Y of t is equal to 3 e to the negative 1/3 t cosine root 3 over 3 t plus 5 root 3 e to the negative 1/3 t sine root 3 over 3 t. And so there we go. And then I just want to talk about one other special case. It's not really that special, it's just it just looks a little weird, but in fact if you carefully examine it, it follows the pattern precisely, and that's where r equals 0. So where we get situations like this will be in differential equations that have this form. So for example, not y equals y double prime plus y prime equals 0, something like that. So then that gives us r squared plus r equals 0, which gives us r equals, here if we factor it, that'll give us r times r plus 1 equals 0, so r equals 0 or negative 1. And for the negative 1 solution here, nothing is different from our usual plan of action, but where r equals 0, it looks a little strange. So what we're going to have then is y equals c1 e to the 0t plus c2 e to the negative t. And that actually, if you examine it, is going to be the same as y equals just c1 plus c2 e to the negative t. And if we had a higher multiplicity value for r equals 0, then that would be a pretty strange looking differential equation, but it would actually still be treatable according to our usual patterns. So special case r equals 0. And this is, and as another example of something like this, let's say we had y double prime just equals 0 by itself. So we have second derivative of y constantly equal to 0. You may already have some ideas about what sorts of functions are capable of satisfying this, but let's just see where our same old methods will take us. So then this means r squared equals 0, which means that r equals 0 multiplicity 2. And so then what's that going to mean? That means y equals c1 e to the 0t plus c2t e to the 0t. But then what does that equal? So the e to the 0 is just going to be equal to 1. So this is c1 plus c2t. Which, sure enough, makes a whole lot of sense. The second derivative of something equals 0. This is the kind of thing whose second derivative will equal 0. You take its derivative once, and the constant term will disappear, and the linear term will become a constant. You take its derivative twice, and everything will end up getting disappearing. So sure enough, this also does fit the pattern. All right. Now, one final note. All of these problems, and by these problems, I mean the problems that either we have just done or any other like them, could also be done by means of making the matrix and using the eigenvalues. So all of these problems can also be solved by the following method. 1. Convert the equation into a system of first order. Equations. 2. Solve the system by our eigenvalue and eigenvector methods. Then the two solutions that you find should be exactly equivalent to each other. And if it's an initial condition problem, so in other words an initial value problem, then they should not only be like equivalent in some general way, but they should be in fact exactly equal. The solution you get by doing this will be equivalent to the solution from the methods of this section. The main advantage to doing it by one method or the other will just be whichever turns out to be easier for the case in question, and that will depend a little bit on the situation. But when you have a system that is just already written as a system, typically the eigenvalue methods will be the easier approach. If you have something that starts off its career as being an equation that you then would turn into a system, then it will often be the case that it'll be easier to approach it through means like this. As you've seen though, sometimes the algebra can get kind of hairy for solving these things when they don't end up with nice clean solutions to their quadratic expressions, but it can always be done, and you can approximate it with a calculator if you need to in order to get a decimal and save yourself some of the messier expressions involving combinations of square roots and fractions and things like that. But ultimately, there are going to be, in general, 3 ways that we'll learn over the course of this class to solve these things, and we now have 2 of them. So if we have a second order system, or second order equation, you can turn it into a system and solve it by the methods of chapter 3. You can solve it by the methods of chapter 4. And it turns out actually that in a later chapter, chapter 6, we'll learn yet another way of solving these things. So this is just our exploration of the many different ways to skin these particular mathematical cats. All right, well, that'll do it for this section. Join me for the next episode of Math 256, where we will explore what happens when these equations are not homogeneous. So if you look at it, every case so far, the differential equation has been equal to 0 and 0. But what if it isn't? That's what we'll learn about next class. So till then, bye.